Hello everyone, this is Jian. I'm very glad to be here and share my research findings at HITV Singapore 2021 today. Really appreciate the opportunity. The topic I would like to share today is going deeper into Schneider Modicon PAC security. Before I begin, I would like to reintroduce myself real quick. My name is Jian from Jian, China, currently an industry control system security researcher and NS focus. The research mainly focuses on PLC, design, SCADA, industrial equipment, and system. Work includes things like vulnerability modeling, industrial field security testing, and evaluation. For the past few years, I reported several vulnerabilities to Siemens, Colossus, Schneider, and so on. Got dozens of CVEs and FOCO, and of course, fax notes from these complaints. As well, I have shared my research at several conferences. This includes China Crunch, SDC 2020, HITB AMS 2021, SS Cybersecurity 2021, and so on. If you have any questions or ideas regarding the security aspect of our industrial control system, please feel free to contact me. Here is my email. I'm looking forward to your emails. Please allow me to introduce our lab, Go Lab, which focuses on SS, IoT, and Internet of Vectors-related security issues. We won the second prize in the Robot Agent Challenge 2018 Jian. Our long-term work in SS vulnerability research results in finding over 50 vulnerabilities in 2020 involving Siemens, Schneider, ABB, Cook, and other manufacturers. In addition, we participated in various competitions such as Fly On and got good results. So here is the outline of today's presentation. First of all, I will introduce the Modicon PAC range of the product application scenarios, the architecture and function of the high-end M5AT family, the security aspects of it, and so on. In the second part, I will introduce the Schneider Priority UMass protocol, its script mechanism, function code, and so on. Next, we will explain fast-related knowledge and for UMass protocol, include how to select symbols, how to build further program, and give you the process of the successful fast demo. The fourth part will be the most interesting part of this presentation, where I will show you how to break through the M5AT password protection mechanism, which includes authorization algorithm, integrity checks, and formats of special function codes to perform sensitive operations such as start and stop the controller. In the next section, we demonstrate a potential ransomware attack on Modicon PAC, including the authorization bypass of the password protection, replacement of the password of attacker's choice, remote code execution, cause permanent damage to the controller, and a brief demo of the attack process. And last but not least, I'm going to talk about how to protect against such attacks. Modicon is the first name in programmable logical controllers. The inventor of the PLC, Modicon introduced the first PLC, the Modicon 048, in 1968. This innovation changed the process design, moving from completely hardware-reliant system to automation system, reducing the time, effort, and cost previously associated with the modifying process. The following years, Schneider helped expand the reach of the Modicon tech knowledge worldwide. Today, the Modicon family continues to push boundaries and define the technology that enables and connects modern machines and processes. The Modicon family of PLCs and programmable automation controllers still stand for innovation, offering a full range of solutions to meet Jian automation needs. To provide an economical way to deliver function control in gap between the PLC and DCS, Schneider offers industrial process automation controller Modicon PACs. Modicon PACs feature redundancy, functionality, negative internet, embedded cybersecurity. Schneider is targeting the PAC towards the process end user, particularly end users who are currently using large PLC or PAC-based systems in energy-intensive industries, such as water, wastewater, food, beverage, upstream and midstream oil and gas, and metals and marine. The ARM microprocessor used in the M5HE PAC is a spell-drawn multi-function CPU built by ST Microelectronics through a partnership with Schneider. The operating system is the Vendriver VxWorks. On the high level of the OS runs encrypted firmware, on the top of which run users' applications. M5HE also provides rich third-party communication functions such as Modbus TCP, Ethernet IP, FTP, HTTP, and so on. To address today's critical cybersecurity issue, security is built into each M5HE PAC to provide an open yet fully secured system. Advanced cybersecurity features help ensure the system are protected from cyber attacks. Each M5HE PAC can be secured using encrypted logins and passwords for every application. Unnecessary devices can be disabled and checks can be performed to verify the integrity of the controller's programming tool and firmware, as well as the normal behavior of the system itself. Based on the previous introduction, we can summarize the attack surface of PAC series products. First of all, the support of the numbers of third-party products make interconnection quite easy, but also introduce risks. For example, each protocol opens external port, which may be bad and taken advantage of by malicious attackers to perform unexpected operations. These protocols include privacy protocols supported by PAC products, HTTP, FTP, and so on. In recent years, many vulnerabilities have been exposed in protocol stacks and operating systems. Therefore, the use of third-party protocol stacks and operating system could potentially bring more serious problems. A vulnerability in VxWorks will affect thousands of devices. Also, physical attacks should not be ignored. M5HE is equipped with USBs. Attackers targeting this kind of hard interface can't be ruled out. We focus on two potential attack vectors in this presentation, though there are many more research aspects. 1. Priority protocol. The reason being that after many research work we find out weak priority protocols are often the best way to break and damage critical infrastructure. Also, faults in priority protocols normally can't be turned off. When you get hands on a device, it's designed to have ports open to support priority protocols, and you can easily access without any extreme configuration. Second, the password protection mechanism. Many industrial control device has its mechanism. Sadly, not many people use this feature in the actual field, despite it being really critical to overall security. Activating this feature will prevent potential unauthorized access and attacks, but nothing is perfect. The password protection mechanism is not an exception either. We conducted several research regarding this feature and gave a presentation on HITB AMS 2021 about the how to bypass such mechanism for Siemens thematic products. Links are provided here. In this presentation, we will dive into the issue of authorization bypass in Schneider's most high-end PAC product, the M5A3. Before we start, here is our research setup. The configuration software is a Control Expert 15.0 SP1. The firmware version is V3.2, and the hardware version of the M5A3 is EP581020. Environment configuration. One PC is installed with the configuration software, and another PC is used to compute paths and write scripts. After connecting to the switch, the two PCs exchange information with the M5A3. Let's start with the first technical part. The priority protocol for Schneider M5A3. The priority protocol used by the configuration software to communication with the M5A3 is UMass. Only field message application survives. This protocol is used by Schneider to configure and monitor the communication between the software and the PAC system, not only in the M5A3, but also in the M340. UMass protocol is based on the Modbus TCP protocol. It's extended on the function code 0x5a reserved by Modbus TCP protocol, and forms its own complete protocol processing system. Next, let's take a look at the UMass format. It's a function code and data part of the Modbus TCP protocol re-encapsulated. The UMass request packet starts with the 0x5a identification byte, followed by a 1-bit reservation flag called CCK. After this, in the specific function code of UMass protocol and the date section. UMass function code varies in different formats, including ID, offset, length, and others. The UMass response package is basically the same as that of the request package. It starts with the 0x5a identifier. The next is the CCK, then the 1-bit error code. It will return FE if the request package can be correctly processed by the controller. The error code is followed by the rest of the digits in the response package. We obtained the function code list inside UMass by reversing engineering the firmware of M5A3, which contains a variety of different operation function code categories, such as operating PLC information, reading a blog, writing a blog, begin upload, and so on. There is a screenshot for some of them with the descriptions. In this list, some function code requires section keys for operations, some don't. So, how is the section key generated? Through analyzing the package, we learned that the visualization and process of the section is like this. Firstly, the client sends the PLC visualization function code 0x10, and the PLC will return a correct reply package. The FE in the reply package is followed by a bit, which is the section key. In the following package interaction, the sensor key must be encapsulated into the corresponding position so that the PLC can handle the operation corresponding to the function code. To facilitate the analysis of the UMass package, we wrote a simple UMass phrasing plugin, which is written in Lua and imported to Wireshark. This enables us to have a clear look at the UMass structure, which contains the culture section key, function code, and data section. By analyzing the UMass protocol, it's found that the structure of the protocol and the procedure matched process is simple. It only needs to send the 0x10 function code and wait for the PAC to return the correct reply, and added the 1 bit to the section key position to establish the correct later on. With such a simple process and message format, are there more vulnerabilities? We then conducted the fast testing against the UMass protocol, where we chose the boot-fast framework and were careful to keep a backup of the fast process traffic in case of the problem reproduced later. In the fast process, we also added a power control unit to improve the fast efficiency. In the fast process, calls the PAC into a fault error mode, which will stop the whole process. The power control unit will restart the PAC again after the execution of fast program, so that you can improve the fast efficiency to achieve the automation of fast process. Before fast, we need to select samples. We divide all functions code of the UMass in two parts. One that requires section key and the other that doesn't. This separation helps us to use different modes for quickly fast. The next step is how to build our fast program. The first step is to construct UMass protocol packets, which differs for different function codes, but the basic method is the same. The other thing is to notice here is that if you need a section key, you need to do something special in order to do a wild fuzz. The second step is to set the section object. The third step is to configure the fuzz target, including the IP address, port number, timeout, and protocol type. Step 4. Add target to the program with the monitor and power control modules. Here is a simple fuzz demo. We found a denial of service vulnerability around 100 seconds that put the device into critical failure mode and require a controller reboot to recover. Okay, let's see it. Oh, the PLC is stop stated, and the fuzz is running. You can see in the below, the PLC, the PAC turn into a critical failure mode and required a controller reboot to recover it. Here are some of the vulnerabilities we discovered using our own fuzz program, which was discovered in January 2020. Okay, moving on to the second part of today's presentation. When we reported a number of the vulnerabilities to Schneider in 2019, Schneider said that they were not vulnerabilities and that they would not exist with an application password. And this time, we found that when the application password is set, the application program compiled and installed the PLC will have password protection, hence unauthorized access will be refused. But what is this password protection mechanism? How to get around this authorization mechanism? So we start this part of the research in 2019. Let's see how we bypass the authorization step by step. The first step is to confirm how the password is stored. The second step is to understand what is the mechanism of the password protection and what algorithms are used. Step 3. After we bypass password protection, is there any other security measures? And if so, how we can break through? Step 4. After all the obstacles are broken, how do we flog a client to perform sensitive operation attacks on the PLC, the PAC or M5AT? Take a look at the first part and find out what form your passwords are stored in. To find out how the passwords are encrypted, I reserve the Unity encryptor.dll file. The encrypted password is delivered in two parts. The first part is an 8-byte random key, which is randomly generated as the result of the hash algorithm. The second part is the value of the SHA-256 using the password and the salt. This result gather with the salt will be stored in the APX project field through base64, which will then be downloaded to PAC with the project fields. The second part is the value of the SHA-256 using the password and the salt. This result, together with the salt, will be stored in the APX project field through base64, which will then be downloaded to PLC with project fields. The second step is to figure out the password protection algorithm, means the authorization algorithm. Here, we analyze the authorization process in M5HA forward to understand how the authorization mechanism works. First, the client randomly generates a 32-byte random value and send it to PAC at the request date. The PAC responds with a 32-byte random value PLC random key. Finally, the client obtains the follow authorization hash through the SHA-256 algorithm based on the input password and two random values. After the hash is delivered to the PAC, the PAC will verify it. So, the key to get around authorization is to find the password salt hash. Where can we get this key? Luckily, we found the password salt hash in the traffic. After analysis, control experts will read the PAC's password hash before authorization, and the PAC will return the password salt hash to the client, so that we can bypass authorization by using this leaked password hash and carry out any operation on PAC, such as start, stop, upload project, and download project. Too simple to be true, right? After testing out, using leakage hash solely to complete the authorization process failed to conduct any sensitive operations, even with the key. What was the problem? By observing the traffic between control experts and M5HA, it's found that a large number of 0x38 packets appear after authorization. The format of the packets is significantly more complex than that our traffic without password protection. Maybe it's the induction of the additional security measures. After our analysis, it's found that the 0x38 function code is a security function code, in which the redundantly part acts as an integrator verification. The integrator check algorithm is shown in the diagram. First, the PLC identity is obtained. It's a unique PAC identifier and can be read through the 0x02 function code. The 32-byte proprietary value in the data package is calculated by SHA-256 multiple checks. UMass MSG is the message body of the UMass protocol. Upon successful authorization, UMass traffic is added with a 32-byte integrity field, and communication with the PAC is done through the 0x38 function code. Here, we take a look at the message format of the 0x38 function code. First, 0x5A and section key parts remain unchanged, followed by the 0x38 function code, followed by security mode 01. The calculated 32-byte integrity field will follow, and finally, the full format of the origin UMAS message. The section key function code is included. Below is a screenshot of the Python implementation 0x38 function code. Now that we have covered all the procedure for our password protection mechanism, let's summarize. First, we can obtain password hash where you must command the memory block rate 0x20. Second, generate 32-byte client random key and then receive challenge key from PAC. Calculate the correct hash value. Third, take PLC reservation where you must command 0x10. Fourth, we need to add a socket layer of integrity check of the 0x38 function code to all the original UMAS message bodies and send them to the PAC at this time. We can perform various sensitive operations: execute, upload program, download program, stop, start, and so on. We were faced with the final problem. of how to make a client to conduct sensitive operations. First, we use a script to achieve the authorization algorithm and integrate the algorithm described above. Then conduct the HR process of authorization and security paths, and finally integrate the start and stop packets into the script. Here we provide a demonstration of a reply attack. The target is a password-protected M5AT. It's impossible to start and stop operations without the correct password. After running our reply attack scripts, the PAC can be manipulated to make it in any stage run or stop. Okay, let's see it. First, we should check the password can be set. If you put in a wrong password, you can't perform stop and start. Okay, running our reply attack script. You can see the PAC can be make any stage run or stop. Yeah, now the PAC is in run stage. So let's continue. In recent years, there can be a variety of ransom incidents. However, these attackers targeting either the IT level in ICS or the servers or PCs in OT environment. Is there a possibility of a ransomware targeting level 1 controllers? There will be. We have proposed such an attack on the controller. Let's see it. To perform this new type of attack targeting Modicon PAC, there are 5 steps. First, invade the OT network. Search for and find edge devices in the network and confirm the attack target. Second, replace the application of the M5AT. Hijack the origin production process and set the attacker's known password. Third, injection shell code to remotely control the controller of M5AT. Fourth, synchronizes send ransom email to enterprise managers, demand a ransom. Fifth, if not paid on time, remote start an M5AT device damage command or instruction. In this attack mode, there are several key technical points in this new attack mode, including applications that bypass authorization and replacement it with a password known to the attacker, and how to perform remote code execution on the M5AT. We are going to demonstrate this tool in a bit. Let's see. Let's start by looking at how to bypass authorization by replacing an application that contains an attacker's known password. Here, a weak password is set just for the sake of the demonstration, whereas in the field it could be too complex to be correct. First of all, let's see it. First, check the version of the control expert. Yeah. Next, confirm that the PAC can set a password. Only the user of the correct password can access the PAC to modify the program or monitor the PLC. After running the attack script, the application program in the PAC was replaced by another machineless one that has nothing to do with the control process, which contains different password. Hence, the original password can't be used to access the controller anymore. Yeah, you can see the wrong password you input. So, access to the controller and program modifications will now require the new password. The new password is we download the project with 1, 2, 3, 4, 5, 6, 7, 7, 8. You can see if we input this password into the PAC, you can perform stop and start. Okay, let's see how we can achieve RCE on M5AT. We can read-write physical memory of the PAC while you must command 0x28 and 0x29, but can't write code segments directly due to page protection. So we can modify the function pager in memory to hijack the control flow, use ROP techniques to complete the code execution. Okay, let's see the demonstration. This is a simple demo for the RC attack. It opens the internal VxWorks WDB debugging interface with a port 171H5 on the M5 HA and show in the above video. Next page. First, use Nmap to scan the debugging port, which turned out to be closed. Yeah, you can check it. The port is closed state. And next, run the POC script. When the POC is running, use Nmap to scan the M580 again. Okay, you can see at this time the port 171H5 is turned on. It's the open state. Okay. Now that we could see a potential attack of this kind, how can we prevent it from happening? We will elaborate from the following aspects. First, we should be able to identify the critical function code involved in dangerous operations and proper runners in our protection devices. For example, runners to identify PLC reservation function code 0x10 in the industrial firewall. Once such packets occurred during normal manufacturing, the traffic should be blocked immediately. Second, we should also focus on the management of our ICS environment. To begin with, all the PLC maintenance personnel should be reliable in case of an insider attack being performed directly to the running PLC. Our adoption should be performed over all operations against the ICS system to prevent malicious maintenance operations, as well as all traffic involving critical devices, so that potential threat could be identified. An access control list can also help to reject access from untrusted IPs. This function is supported by M5 HA. You can open it and enable it. Third, for ICS manufacturing, not only Schneider and Siemens, many privacy protocols are really weak with such simple authorization algorithm. Therefore, manufacturers should pay attention to the following aspects to stressing the controller security. There is some suggestion of we can say it. First, and a mature authorization mechanism for privacy protocols. Second, use strong encryption algorithm. Third, avoid information disclosure. Fourth, password authorization should be performed in PLC or PAC. Fifth, sensitive information should be stored in a trusted zone where it is reinforced. Okay, actually, there is no standard for PLC coding. VVK and Sarah lead the PLC Security Top 20 list project and released the first version on June 15. It's a pleasure that I was invited to join the core group of this organization to discuss project on PLC security coding. Well, PLC security coding can't solve all the network attacks. It can solve many problems caused by misconfiguration or insecure hiding of users' inputs and so on. And at present, this project still has a lot of work to do, including top 20 secure PLC environment practice and the PLC security top 20 list with the version should be upgraded. Anyone who is interested in the topic is welcomed, and we look forward to your joining. Welcome to join us. Okay, that's all for today's presentation. Thank you all for joining the talk. If you have any question, please feel free to contact me. Thank you. Bye-bye.